That's our cue. Good afternoon, everyone. Everyone's still awake? Everyone's surviving? Looking forward to some more fun tonight, I suppose. My name is Grant McAllister. I'm a senior principal engineer with AWS. I work on the Amazon RDS team. Today we're going to do a deep dive into our use of Postgres and our newest features that we've just announced in the last couple days, as well as some of the learnings that we've had over the last year running Postgres for our customers and helping them manage it. And I'm also very happy to have Greg Roberts here, who's going to talk about his experience using Amazon RDS and the Postgres edition specifically. So let's dive right in. Okay. Maybe it's not working. Okay. Yeah. Sorry, technical stuff. Okay, we'll just do it the old-fashioned way. So one of the things that we get a lot with our customers is talking about data movement. How do I get data in and out of RDS? How do I, connect my database to other things? So we had a lot of questions, so we wanted to cover this, this topic. So you probably get a lot of blogs out there that say, here's how to load data. Some of the standard things are, if you're doing a full big database load, you want to disable your backups. You want to turn off our multi-AZ feature. You want to turn off auto vacuum. If you're using PgDump, you want to use the compression, the big capital F, little c. And if you're doing the restore with PgRestore, you want to use the -J option, which really get you parallelism on like building indexes and other actions like that. You want to increase your maintenance work memory, because we set the default to 16 meg, because we don't know how big of indexes and other things you're going to do. And I'll actually show you some examples of that. And then the other one that we really recommend is increasing the checkpoint segments and the checkpoint timeout. And this is how often your database is going to checkpoint. Now, one of the other things that you'll see a lot in the blogs is disabling fsync. Now, how many people in the audience know what disabling fsync does? So a few of you. So what you're basically telling your database, don't immediately sync this stuff that I just changed to disk. Do it whenever, sort of convenient for you. So you imagine if that database reboots or that system crashes, what's going to happen? It's going to leave your database in an inconsistent state. So not just the table you were loading, but possibly system tables. If you were creating an extension, it'll have all kinds of weird effects. So in reality, we don't like that recommendation because we think it's not actually that useful. Instead, what I recommend is disabling synchronous commit. And how many people have used that feature? A few? So this is the safe way to get the same effect. Essentially, you're just telling the database, bundle a bunch of stuff up, but do it in a strictly consistent fashion. So even if you crash, you'll just lose the last couple records, not corrupt your whole database. So I wanted to show this as an actual real benchmark example, not just theoretical. So I took a 32-way insert test with fsync on and fsync off, synchronous commit off. And so this is a transactions per second on the vertical axis. So obviously bigger is better. And you can see when we start with both of them turned on, I actually ran the test with both 16 checkpoint segments and 256. And so that the 256 is in that sort of purplish color. So when we turn fsync off, you see we get a lot of improvement, which is why the blog posts all say to do this, right? Because it makes things go faster. But guess what? If we turn that back on and we turn synchronous commit off, it's actually faster than fsync off, which is kind of interesting, right? And I was actually talking to the person that committed this for Postgres, and he was like, thank you very much. He's been trying to tell people about this for a long time. He was very happy to see this. Now, you can turn both of them off and you get a slight performance improvement. But look, it's really only 4%. Are you going to risk your whole database being corrupted for 4 more percent? I mean, it's an option, but it's not one that we really think you should be using. Because look, you get 104% improvement by just doing synchronous commit off. So what about big data loads? Now this is a little different, right? You're doing a bulk load. If you do this, you can actually see when we go and we use 256 checkpoint segments, we get a big reduction, almost 40%. So that's an actual real parameter you want to change when you're doing this kind of work. Now, if we do turn fsync off, look, not really much improvement. And even synchronous commit doesn't make much difference here because you're only really doing one big load, right? And turning them both off, again, a little bit of improvement. But we're talking 3% again. So again, probably not worth to make that change. You're better off just having more checkpoint segments. So someone said, well, what about on index builds? So we did the same thing. Now again, these ones are timed, so we want them to be smaller, just like in the last example. And I started out with the maintenance work memory set to the minimum, 16 meg, right? And the checkpoint segment set to 16 as well. And you can see with fsync turned off, where fsync equals 0, we saw a whole 30 seconds of improvement, or not even that, not much. Now look at when we go and change the maintenance work memory to a gig. We see a nice reduction, right? And if we change the checkpoint segments to 1024, we actually see another great improvement. So this is really just showing you that, depending on the action you're taking, you really want to look at the parameters and you want to do a bunch of testing. And the great thing about RDS is you can take your production system, you can make a copy of it, couple clicks, and then you can run with these new parameters and test all of it. It's very simple. I also get a lot of customers say, well, should I just set the parameters really large? I'm on a big box, I got 200 gig of RAM. Should I set, my maintenance work memory to 100 gig? I don't know. So I ran this test where I did an index build on a 20 gig table. I started out with the default of 16 meg for the maintenance work memory, and you can see I got 29 minutes. When I increase it to 4 gig, I get a slight improvement, but I only got a minute back. It's kind of odd. So I thought, well, what about on just a gig? And it's faster, right? Now, this is going to depend on your system and what you're doing, but even 512 turned out to be a little faster. So, it's not necessarily that you always want to set your parameters really large. You want to test them. Now, everybody's system is different. How many processors you have, how much parallelization you can do, that all depends, right? But you really want to test all these things out. The other one we get a lot of questions about is vacuuming. So I did that insert. I've loaded my tables, but I didn't do any updates or deletes, so I shouldn't need to vacuum, right? So I was running 100% read-only workload. And you can see the green line is write IOPS, and this is CloudWatch metrics that you can get with RDS. And you'll notice I start that test off, I'm getting 21,000 transactions per second, which is quite great, but I'm doing like 5,000 writes per second. What's going on here? Well, Postgres leaves rows in states where at some point it wants to flush them back out, and this one specifically is called hint bits, and I won't go into all the details, you can read about it in the manual, but what we needed to do is we need to actually vacuum the table out. And so I stop the test, I do a vacuum, and you can see how much work it's doing because it's up to 20,000, doing 20,000 IOPS to get that out. And then once that's done, you can see in that pink area, I reran my read test. I get 45,000 transactions per second. So a dramatic difference because what Postgres was doing was, as it was reading those blocks, it was writing them back out, some of them. So now it doesn't have to do that, it can run much faster. So you really want to pay attention to a lot of your vacuum settings in Postgres because otherwise you're actually going to have lower performance. So what do you really want to look at when you're setting these? Well, first you can do vacuuming yourself manually, but a lot of people just rely on the auto vacuum function. It will basically kick in when you have the vacuum threshold plus the scale factor basically hit on a table. And that is it defaults to 20% out of the box. So the PG class rel tuples is essentially how many rows you have in your table. If more than 20% of them change, then it's going to vacuum your table. The vacuum threshold, I think, is set to 50, so it's actually, unless you have a tiny table, it doesn't even really come into account. And then the other parameters you want to look at is how hard auto vacuum will actually run. And this is kind of interesting because there's a lot of little settings here, which if you don't tune, you probably won't get through vacuuming all your tables on a regular basis. So the number of workers you can do, so amount of parallelism. The nap time, it'll stop after each time it does a vacuum. And if you set that to like a day, you'll get one vacuum done a day, right? The cost limit and cost delay, basically, how hard will auto vacuum work? So every time it looks at a row, that is a particular cost. Higher cost if it's on disk, lower if it's in memory. And then when it hits that limit, it delays, so it sleeps for some number of milliseconds. So in this you can tune so it can take a long time but be very smooth on your system, or you can have it work harder. So it's really things that you want to really set. One of the other new parameters that we introduced, new extensions we introduced on this Monday with our latest release of 9.3.5 is Postgres FDW. Now this is a really nice extension because it allows you to basically read or write to other databases that are Postgres or Postgres front ends. And I thought, well, what better way to show this than to use Amazon Redshift, because it has a Postgres front end, and we can see how you might integrate that with your regular Postgres database. So I created an extension, and you can see here that, redshift.amazonaws.com. So I'm actually connecting to a real Redshift instance. I go create the user mapping and the foreign table definition, and I can do a count from that table. Now, I didn't have a lot of data in there, but I can also insert, which is kind of interesting. So this is a way for you to basically move data in and out of RDS and to link to other databases. And I think having Redshift tables available in your application is a really kind of cool way to have data warehousing and not have to go make another connection for your application. One of the other things we added was support for the session replication role, which is actually not a role, it's an actual session-based parameter, which I really like. And this is essentially used by all the third-party replication tools for Postgres, pretty much. And what it does is it really helps you deal with triggers and replication. And I'll show a little example here. So assume you have two databases, you have two tables, and you're basically triggering inserts into each other across them, let's say with an FDW. So if you were to do an insert into one of these, that insert's going to go into the table and fire the trigger, right? Well, that trigger is going to go and basically loop it around and insert it into the other table, and that trigger is going to fire, and it's going to go around in that circle forever. Or if you had a primary key, you'd get a nice little error. So what the session replication role does is allows you to say, don't fire triggers depending on what that role is set to. So why do you care about this? Well, because it allows us to support things like Bucardo, Londist, and some of the other third-party replication tools. So in this example, I installed Bucardo on an Amazon EC2 instance. Why did I do that instead of RDS? Well, it requires the PL Perl U, the unsafe version of Perl, which we don't support inside of RDS. But Bucardo is nice because it reaches out and talks to things. So you can have an RDS instance that you can basically replicate into, out of, or even multi-master. So that's actually a really nice way if you need to move data into RDS, or you want to run sort of a hybrid mode where you have an RDS instance plus an on-premise or an EC2 instance. Now, some people will say, well, what about if I want multi-master between two RDS instances? Well, it's not possible to do directly, but again, you can use Bucardo as to be the thing in between them, and you can actually do this. And I set this up, and it was running great and worked really nicely. So there are sort of opportunities. Now, I'm not an expert on any of these sort of third-party tools, but Londist and some of these other ones, they definitely they work with the session replication role. So let's jump into scale and availability. So again, we have a lot of customers that have questions about that. And one of the big announcements that we made was support for read replicas on Monday. So this is a really great feature that we've had in the MySQL engine for a while, and that we wanted to have for Postgres as well. So our general story on availability is we like our multi-AZ product. It's synchronous replication. What's nice about synchronous replication is we know your data is going to be on the secondary. So there's no data loss when you want to fail over, right? So that's great, but some people say, look, I need even higher availability than that. I need to have high read availability. So let's say you have a blog application. Most of your people coming in are only doing reads. There's a few people that are probably writing blogs, but probably 95, 99% of them are doing reads. So what you can do for that kind of application is you can create one or more read replicas, and this is Postgres, streaming asynchronous replication that you would use today with Postgres. And you have to change your application, obviously, so that it does the eventually consistent reads over to the read replicas, and you still want the writes and the reads that need to read those writes to come from the primary. But the way this works and how it helps with availability is, let's say something happens to your primary. Well, we're going to fail that over, but that takes about 60 seconds to happen. So while that's happening, you can't write. But the nice thing is, hey, your blog application is still working because most of the people are just doing reading, right? And this goes the same, once the database fails over, you can write again, and we're going to stream those changes over to the secondary, so you're all back together. And this is if you're doing, let's say, upgrades. You can use the same model where you can keep reading while you're doing a change or an upgrade to your database or your application. And of course, because you can have more than one read replica, you can upgrade them at different times, so you can sort of roll through them. So it's a nice way to add availability to your application. The other thing that read replicas are used for is scale. A lot of people do scale out with these. So for example, in a lot of our regions, we have one or more availability zones, and this one I'm showing 3 fake AZs. And you normally start off with the one database, the one application running against it. And of course, we recommend that you have multi-AZ running again. and you have multiple application servers in each of the availability zones. But now each of those can go and read from a local read replica, so the latency is really good, and you can get scale out of it. And you can have, this is just showing one in each, but you could have them all in one. It's very flexible that way. Now, one of the things to think about when you're using read replicas for scale is how much writing am I doing? Because let's say you have an example where you have 90% reads and 10% writes. If you go and do 4 replicas, you're going to be able to move a lot of that read workload to those, right? But remember that the writes still have to go through and be done on, all those replicas. Now, it's maybe not quite as expensive as it is on the primary, because you're not parsing and doing all that, but you still have to do those physical writes. So when you scale, you're basically adding more to each one. So in this case, you can see with a 90% read ratio, we can actually get pretty good scale out of it. We can get a 3x scale number. But on the other hand, for example, if you had the yellow line here where it's 50% write, guess what? Read replicas is not going to do a lot for you. You'd have to use something like 32 nodes to get 2x scale. It's not a very good deal. So, and I showed 10% here, but you can imagine if you had 99% reads, you would get a lot better scale. So we have a lot of customers that use this in MySQL very successfully for scale. The one thing I did want to cover was how we do promotions, which is a little different than you might see on-premise or on EC2. So let's say we have a read replica that we want to make into a reporting node. Well, you can always just do a restore, but one of the nice things about having as a read replica is it's always caught up, right? So it's right up to date. You don't have to wait for a restore to happen. So let's say we want to promote that one. Well, when we run that promote call, we get a new primary. Now you can make this multi-AZ, you can create read replicas off of it, but the important note is, notice that nothing else changed in that setup. We didn't change any of the other read replicas, we didn't parent them to this replica, we didn't change anything about your multi-AZ setup. And of course, you can just go put a new application, points to a new CNAME, and you're off and running. Now, there's some very important sort of parameters to think about when you think about using streaming replication with Postgres. And the big one that we see is wall keep segments. And how this works is, when you're streaming, you don't really care about where your logs are because it's being streamed. There is no log shipping. But let's say that replication link breaks for a little bit because the network's having a little problem. Well, you're going to start accumulating logs on the primary. So you're going to keep doing this. And let's say you have the wall keep segment set to 98. Well, when you hit 99 logs, Postgres wants to start removing them to clean it up space. Well, the nice thing with RDS, of course, is that we actually put them in the cloud. We back them up all the time for you. So we can manually apply those on the read replica. And even though it's removed from the primary, it's going to get shipped down to the read replica where it can get applied. So this is how we do catch-up. And this is a really nice feature because it means even if you run out of space, we will catch you up. But during that time, you're going to be into log apply. So it's going to be, your lag is going to be greater. So the trade-off on wall keep segments is when the replication comes back together, it'll take you a little longer to catch up. So it's a space trade-off. Now, segments are only 16 meg. And you really want to think about how much space that you'd like to trade off so that your streaming replication will basically come back sooner in the case of some disruption. The other replication parameters that are really important is how this replicas work with queries. So in this example, I have a source and a replica, and it has a table, and it has a row in there with a primary key of A and a text of foo. Let's say I run a long-running query on my replica. Select from T1. Now, no one's ever had a user that forgot to do a where clause, have they? Nah, it's never happened on your database, right? So this thing's going to take hours to run, for example. Well, what happens if we go do an update to that row on the source? Well, for Postgres, how it does its MVCC is to essentially make a new row and keep the old one around to satisfy any queries. So that's what it looks like. We end up that new row called a-bar. This, of course, is going to be replicated down to a replica, just like you'd expect. No problem there. But let's say the administrator decides to do a vacuum on that table. Well, that vacuum is going to remove that old row because it's not needed. There was nobody querying it on the old source. Now the replication kicks in. That's going to replicate basically the removal of that row. When that happens, this is what happens. That query that was running for an hour gets broken, and you get this nice error. And it didn't just break your query, it broke your connection, actually. So how can you deal with this? Well, I mean, you could not run long-running queries on your replica, but that may not always be possible. So there's 3 key parameters, and they all kind of function differently, but they're all trade-offs. Vacuum defer cleanup age essentially says to wait, whatever amount of time you set before the vacuum will kick in on the primary. So that will basically, cause a little more bloat to happen. Max standby streaming delay will actually say, don't apply a change on the replica that will break a query for this amount of time. So of course the bad part about that is it's going to cause replica lag. And then the third one is hot standby feedback, where the replica basically sends information back to the source and says, hey, I have this long-running query, don't vacuum this information because I still need it. And that will also cause bloat. So you really have to play with these and trade them off on how much space you want to use, how much delay you want to have. But this one's actually really key to having good success with replicas. And of course, now that we support replication, we also support the PGStat replication view. And you can see here, just an example, hey, the state is streaming, so you get some nice information feedback on the state. We also have a CloudWatch metric that shows the lag of your replicas, so you can monitor it that way as well. And of course, all this benchmark and everything I did, how did I look at all those numbers? How did I see what was going on? I used the extension PGStat statements, and we just introduced support for that. How do you get this configured on your RDS instance? Change your parameter group to add it as a shared preload library. Once you've done that, you can start using it. And it's super handy for really tuning and seeing what's going on in your database. The old method was to turn on a lot of logging, dump it to the log, then post-process the log. This is super nice because it's all there in your database ready to go. There's a bunch of parameters as well that you can tune this with. I think there's like 4 parameters that change sort of the settings as well. So other things that we've done in 9.3.5, we support PLv8 now, the JavaScript engine, so that's really nice. The test parser extension. Now I know all of you are really excited about this. How many people know what that does? Almost nobody? Yeah, I didn't know what it did either, and our customer said, look, we don't use it much, but we use it to do some validation. So we were like, great, we'll put it in with this release. So that was nice. We put a new version of PostGIS into the build that fixed a few bugs, as well as we added support for grid shift files, which I still don't understand what that does, but it's a good feature. And then, of course, we support shared preload libraries, but at the moment, the only one we support is PgStatementStats, but in the future, we'll be able to add other ones as customers sort of give us feedback on other things they'd like to see. Now, I wanted to cover some stuff that's a little more general, not specific on Postgres, and it's really about burst mode computing, because this is something we've rolled out over the last year that I think is really important for all of our customers, especially from a deep perspective, to understand how these things work, because I think there's a ton of leverage here for you from a sort of price performance perspective. So we have 2 basic additions, the GP2 storage type from EBS that we support. And it's an SSD one, much like the provisioned IOPS model, except for instead of specifying how many IOPS you want, you just tell us how much storage. And then you get 3 IOPS per gig. So you buy 100 gig, you get a regular steady state of 300 IOPS. Now, if you don't use all 300 IOPS, they sort of go into your piggy bank, and then you can use them back up. You can burst basically to at least 3,000 or higher, depending upon the size. And I'll show you how that looks. And then on the EC2 side, we have the T2 line, which we start as a DB2 micro, small, and medium. And these do the same thing where you have base CPU credits. If you use them all up, it's great. But if you don't, you get to spend them later, and you get to burst. And the thing I really like about the T2 is there's actually a CloudWatch metric that shows you that, which I'll show you an example. So this is actually running a real benchmark of a read workload where we start off getting really good performance, 6,000 transactions per second. Really quite remarkable. This is a T2 medium with a 200 gig GP2 volume or size. So what happened on that first drop? Well, that's when we ran out of GP2 credits. So you can see that there's dramatic reduction, but hey, look, we ran for almost 2 hours before that happened. And then I run a long, long time, many hours, before I exhaust the T2 credits. So then I drop down to 2,200. Now this seems like a big drop, but still, it's actually doing quite a bit of good work for me there. How do I see how I'm exhausting the credits on the T2? Well, there's a nice little graph, and you can see since I was doing a steady state test, my CPU credit balance just slowly drops in the yellow there as we go on until it hits 0. And then you can see from the CPU graph in the green how it basically drops down quite a bit. Now, that's all nice, but why do you care about this? Well, it's about price performance. So I took an older model, one of our past generation systems, a DB M1 medium, 4 gig of RAM, and I had a 200 gig standard magnetic storage on it. So this is what we used to have, everybody runs, still a lot of our customers run it. And I ran this benchmark, I got about 1,200 TPS out of it. And the cost was about 57.5 cents an hour. One of the reasons why it was so expensive is it's a past generation system, but also because you get charged per IOP, well, per million IOPS, on the standard EBS. So this is going to add up if you're actually doing a lot of IOPS, which I was in this test. So I said, well, okay, let's go use a more modern system, one of our M3 mediums. And this time I used the provisioned IOPS, and I bought 200 gig with 2,000 IOPS. And you can see I got double the performance, and wait, I'm spending less money. So it does show that sometimes, depending on what you're doing, you definitely want to pick up the newer models of our fleet. I noticed that I was a little CPU bound on this test, so I thought, well, let's throw an M3 large at it. So that's the next jump up. It's got a little more RAM as well. So I got a little more, got up to 3,000, but I was basically running out of IOPS there. So I wasn't going to get a lot better, but still a good improvement. And if you actually look at it, the price performance is about the same. Now let's go look at the T2s. So the first one I picked was that T2 medium with the 200 gigs of GP2 storage. What was very interesting about on this particular test, which is a little different than the previous one, is that I get really good performance right off the bat. More than 3,500 transactions per second. And the remarkable thing, look at that cost. It's 10.5 cents an hour. That's almost a quarter of the cost of the medium, the M3 medium. So that's remarkable. Now it does drop down after a couple of hours, and I'm not getting that great performance now. I'm getting, less than 1,000. So I said to myself, well, the nice thing about GP2 is if I want more IOPS, all I have to do is buy more space. So I went and provisioned one with a terabyte instead, and that's in the gray. So you can see now, the cost went up. We're now paying 23.3 cents an hour, but look at that, we got 6,000 transactions per second until we hit the first cap on the GP2. So even when it dropped down, we're still at 4,000, and look at how many hours we're at that. So you go to almost 18 hours of sustained, really good performance, better than any of the other options. And even when we drop down right at the end, notice that we're still almost the same as the M3 medium. And look at the price difference there. It's almost half the cost. So even when it was not bursting, it's still great economics. And when it is bursting, it's unbelievable economics. So now whether a T2 fits you or a GP2 does, but I would definitely check them out, especially the GP2 if you're using magnetic today. It's a great option to get you basically more performance for a lower cost. So you'll actually save money by running GP2 for most database workloads over magnetic. So we're really encouraging customers to go check that out. And with that, I'm going to turn it over to Greg, who's going to talk about his experience with RDS.
Great. Thank you. Everyone, I'm Greg Roberts. I'm the Associate Director of Cloud Computing at Illumina. How many people have heard of DNA? Okay, I'm assuming there's more people than that, but how many people have heard of Illumina before it just got brought up today? A couple people. So for the people that haven't heard of DNA, come see me after this talk and I'll fill you in. But Illumina is the leading provider of genomic sequencing and array technologies. So we like to say that almost more than 90% of the world's bases that are sequenced throughout the world are done on our technology. So if you've ever ran into anywhere where you've gotten sequenced or genotyped, it probably happened on one of our instruments. It's also interesting to know that earlier in this year we announced what we call the HiSeq X, which was the first instrument that's capable of producing a $1,000 genome. This may not seem too interesting to some people, but if you look at Moore's law compared to what we call a Flatley's law, about 10 or 12 years ago, the first genome that was sequenced cost about $100 million. So the price drop of how sequencing has been progressing has been outpacing Moore's law for a while now. And the other interesting thing is that genomics is really big data. So if I were to get my full DNA sequenced, it would be about 300 to 500 gigabytes of raw data. And one of our really high-end instruments can produce about 1.5 to 1.8 terabytes in a couple days. So you can imagine you've just bought a bunch of these sequencers, and now you have a data problem. So Illumina's answer to that data problem is a product or a service that we call BaseSpace. And this is a service that we run in AWS. It does several things for our users. One of the things is it is instrument management. So setting up your sequencer and monitoring and all that, you sort of have that tight integration. The unique thing about our platform is as the data is being produced, that 1.8 terabytes or less, it's constantly being streamed to AWS, so we don't wait till the very end to actually put all that data into the system. It's sort of, we can keep up with the sequencer because it's just sort of falling off. So for our customers, a big part of what we're offering them is data management and sharing. So if I've got one of these 400 gigabyte data sets, I can just create a share link, much like you can in Dropbox or Box, and give other researchers access to it. And the reason why I'm here today is to talk about one of the components of sort of the third tier of what BaseSpace is doing is it's an application platform. So when we first started out about 3 years ago, we initially launched an API, much like Facebook or Twitter API, that allows other websites to sort of integrate with our system. But it was really for desktop and web applications to integrate. And really for genomics researchers, what they want to do is create algorithms, package those up, and run them with the data. So we needed to come up with a way for those algorithms to get packaged up and run securely in our system. Around that time is when Docker was announced, so it was sort of dumb luck for us that technology was just getting started and getting popular when we decided that we were going to build this framework. So the three components of the native app engine, one is the sort of input form, so we have a declarative syntax that people can use to create sort of their sets of inputs. Then we have their Docker image when we host our own private registry for the Docker containers. And then we have a report generation mechanism. So you kind of put all those things together, and it gives our developers a nice way to sort of package up an analysis. That's a picture of our developer portal. So one of the key systems that we needed to build to sort of make all this glue work is something that we call mission control. And mission control is very simply just a Docker job scheduler. So on Amazon, obviously you're not dealing with Docker, you're dealing with EC2 and AMIs. So the sort of overarching goal of this is to be really simple. So we, like a lot of cloud providers, we produce these sort of purpose-built services instead of a monolithic service. So we needed something very simple. We wanted everything to be very, ACID and transactional. We have semi-structured and relational data. So we sort of package all that up into an API service that's running on Amazon. We're using Postgres RDS as our back end. We're using multi-AZ for all the reasons that Grant talked about. And then on the sort of what is running side, the native app AMI, we have Docker, and then we have a custom-built Fuse driver and our little service called SpaceDock that's sort of doing a bunch of magic to make all this stuff work. And if you want to learn more there, if you just Google developer BaseSpace, you'll find more about that. So some of the reasons why we chose Postgres, there's a lot more than I've listed here. General performance and compression is really good in Postgres. So a lot of times you have to tweak other, if I'm talking about mostly open source data systems like MySQL, you can do compression now, but it's not on by default, so it's one of the things we like. For us, coming from maybe an Oracle SQL Server world, it's weird to me that you don't have transactional DDL in some systems. So I think even before MySQL 5, 6, you couldn't even do a lot of online transactional statements, like adding a column or something. So in Postgres, if you say you want these 3 columns added, and if one of them fails, you don't want any of them added, then that's transactional DDL, which is very nice. The type system in Postgres is really pretty cool. They have JSON, the HStore, which is sort of a dictionary format, Geo, which is powered by PostGIS, arrays. So for us, JSON was really important because that's sort of how some of our jobs get declared. So we have part of our schema has this sort of, JSON-based part to it. And the other thing that a lot of people maybe don't consider, or for the cloud, it's maybe not as important, is licensing. So Postgres is BSD. Some of the other database engines are either just totally proprietary or GPL. For us, we actually package up base and sell it as an appliance. So it's really important that we make technology decisions that can work on that appliance without too many legal concerns. And then I think an unspoken sort of momentum. I think there's a lot of stuff going on with Postgres. So if you've ever heard people talk from Instagram and stuff, there's a lot of interesting things going around with the use of Postgres. And then on the RDS side, so I'm a developer. I'm not a Postgres DBA or anything. And one of the things I loved about RDS when we first started using it was all these complex, multi-standby, hot standby and read replicas and all that, 5 years ago, if you would have done that in a small shop, you were doing something pretty advanced. But a couple clicks of a mouse and you have this pretty fault-tolerant system set up is really powerful. So I wouldn't say you're not going to have a DBA in your team, but it eliminates a lot of the typical things that a DBA may have to do. So like I said, the complex configurations. Another thing that isn't always the easiest is upgrades. So if you've been using any of the systems in RDS for a while, they make it really easy to get to the next version, and the next version is usually available pretty soon after when it's released. And then finally, automated backups and restore. Anybody that's running any transactional system, you really need automated backups. It's just another mouse click or CLI call. We often will, before we test big releases that have a lot of migrations in them, we'll restore a backup of the latest and sort of test out everything and shut it down. Or you can spin up replicas and make those changes there and then switch it over. For us, the transition to RDS was pretty smooth. When this project got started, it was maybe 6 months before they announced that Postgres support was there. So we had just started sort of doing some stuff in production on Postgres. We were using previously another SaaS provider, Enterprise DB, and they were sort of hosting our stuff on EC2. There wasn't necessarily anything wrong with it, but it didn't have a lot of the benefits that we know we could get from RDS. So we just did a very standard PG dump and load when that time came to transfer over. The setup that we've sort of now landed on is a M3 2X large multi-AZ. It's got about 30 gigs of RAM, and we've got about 400 gigs of storage of 4,000 IOPS. The two sort of alarms that I set usually on these is high CPU and low disk space. I mean, obviously low disk space, you don't want to run out of disk space. High CPU, I think it's good to know because a lot of times there's an application issue if you're really spiking at more than 80% CPU for and you didn't know about it. So for performance tuning, there's a couple tools at your disposal, and I'm not going to go into a lot of the complex stuff that Grant went into, but I think it's really good just for normal developers to kind of understand that performance tuning and benchmarking is really easy. And there's a couple tools, readily available that make it easy, and there's a lot of stuff that you can do more advanced. PgTune is just a sort of recommendation tool that's been converted into a simple website. So if you just put in how many CPUs, how much memory, it'll just sort of spit out, well, this is the general sort of settings that maybe you should think about. And PgBench is just a very simple command line that will throw load at a server, and it's got a bunch of different options on the schema that you wanted to look at and how many, do you want it to use transactions or how many threads and all that do you want it to use. So I'm going to go over some of the things that I found regarded to the setup that we ended up changing, the defaults. And overall, I think most of the settings that Postgres has on RDS are pretty good, but I think some of them are a little conservative. One of the things that I think everybody should look at is the max connection. So by default, RDS is looking at the memory size and not the sort of CPU configuration. So a lot of the recommendations that I've seen sort of everything's application specific, but a lot of it's also specific to how many CPUs you have. So I think the default that you got was probably too many connections set, so we had lowered that for our instance type. Shared buffers, most of the literature you read around is about 25% to 40% of your memory. So we kept the same there, but you can definitely test out your different setup. Working memory, this is sort of tied to how many max connections you have. So this is how much memory a connection will actually take up. And if you have too less, then you might end up running into issues. And if you have too much, then you're allocating too much memory per connection. So for us, that we changed the default from 1 to 3. And the last one I think that's really worth bringing up is the maintenance work mem. This one is set to the engine default, which is 16 megabytes, which was probably set, I don't know, 8 years ago when machines didn't have a lot of memory. This is something that you really need to sort of be aware of when you are making big schema changes or adding indexes and stuff like this, because this is how much memory do you give that process to carry on that. So 16 megs, and Grant showed a very good sort of bar graph of it. Sometimes it's very particular to what you're changing. But I think, just coming into this new, it's something that, hey, why did that index take so long to create? This is something I would look at and say, well, maybe that, can be increased. And then finally, I did a really simple PgBench just to sort of show how easy some of this stuff is. So when we were initially transitioning from the older instance types to the new instance type, I was just curious, if I did a very simple test, what would the performance difference be? And obviously Amazon makes this type of stuff really easy. Just spin up a couple EC2 nodes, spin up a couple RDS nodes, and now you've got your test set up. So for us, we were just comparing the M2 2x large, M3 2x large. It's a little unfair because the CPUs and stuff, obviously changed. So you would expect that the newer ones would be faster. And indeed it was. And this is the simple command line that we ran just to do a single-threaded sort of how many inserts can we do and how fast can I get done. This is a very simplistic example. A lot of what the PgBench tool will actually do is set up the schema, and then you can do a lot of different queries, and you can track the transactions per second and all that. But I think for Postgres sort of newbies, this is something of interest. So that's all I have. One note is, Illumina and BaseSpace, we're always looking for good engineers. So if you guys are interested, please come talk to me after this.
Thank you, Greg. So I think we have a little bit of time. We can take a few questions. I would remind everyone to give us feedback on the talks. We really appreciate that. So if you get a chance, go online and do that. Have any questions? No. Go ahead. So the question is how to set up read slaves? Yeah, the question was about how to set up read replicas, as we call them, for Postgres. You have to make sure you're selecting that you have to be on 9.3.5. It's the only release that's available, so it'll be grayed out if you're on like 9.3.1 or through 9.3.3. That's probably yeah. Any other questions? Go ahead. Yes. I didn't quite catch that last part. So, right. So the question about just, setting the disk-based checksumming on for Postgres, is that the question? Right. Yeah. So yeah, by default, RDS turns on the that checksums for all the instances. We believe that even though there's a little overhead, you really want to know if there's something going wrong with your system in any way. And I was actually really happy because when we first started looking at Postgres, we got lucky that 9.3 was the release that came in, which was our first release. So, because of course, even if you upgrade from 9.2 to 9.3, you won't get that because it's only on new crates that you can do it. So if you are doing that, you'll need to do a dump and load. Luckily for us, we started on the version that supported it. So, cool. Other questions? Go ahead. Yes, so the question is around the Postgres integration with Redshift. So I wouldn't say it's integration per se, but I mean, the nice thing about the Postgres FDW extension is it'll allow you to connect to anything. So literally what was on my slide, you just go in, you can do, I mean, you need to do it as the RDS super user, which is the privileged account that you get when you create the instance. But once you've done that, yeah, you can select or insert data. So, you could have a, petabyte Redshift cluster, and you could have that, let's say there's a table that's a petabyte, you could be able to do selections from it. Now, of course, Redshift has slightly different semantics and slightly different data types in some cases than standard Postgres, so you can't necessarily have it, everything be exactly the same, and there will be some language restrictions. The question is, can you join tables between them? As much as Postgres FDW supports. So I believe the answer is yes, but I don't know to what level of complexity that occurs. But good question. Any other questions? Sorry, the question about supporting beta releases? We currently don't have any plans to support beta releases. In general, we try to get the new versions out as soon as possible after the release, and part of the challenge is with a beta release, sometimes they tell you, by the way, everything you put in there, you've got to remove, which is tough for us as a managed service where our customers may not quite understand that challenge. So. Ooh. Any other questions? We'll be available outside if anyone has anything else they'd like to talk about it. And obviously there's down in the exhibition hall, there's a database booth where you can come talk to my colleagues about RDS, DynamoDB, Redshift, Elasticache, or any of the other database services that we vend. Thank you again.